Hi, I'm Andrew, and this is part 10 in my Advent of Code series, where every day I'm attempting to solve a new code challenge. Previous videos are up on my channel in a playlist called Advent of Code 2022, and if I'm able to solve any challenge for the day, the code that I write, I will upload to my public repository. The link for that is in the description for the video. For today, let's go ahead and get started. We have a cathode ray tube. You avoid the ropes, plunge into the river, and swim to shore from our last challenge. The elves yell something about meeting back up with them upriver. The river is too loud to tell exactly what they're saying, so they finish crossing the bridge and disappear. Situations like this must be why the elves prioritize getting the communication system on your handheld device working. Also from another challenge, you pull it out of your pack, but the amount of water slowly draining from a big crack in its screen tells you it probably won't be much use. Unless, that is, we can design a replacement for this device's video system. Okay, it seems like to be some kind of cathode ray tube, screen, and simple CPU. They're both driven by a precise clock circuit. The clock circuit ticks at a constant rate. Each tick is called a cycle. So we need to start by figuring out the cycle, or the signal, being sent by the CPU. The CPU has a single register X, which starts with the value 1. It only supports two instructions. Add X, V takes 2 cycles to complete. After 2 cycles, the X register is increased by the value of V. So the V is a variable and add X is the command. And then no-op takes 1 cycle to complete and it has no other effect. Okay. The CPU uses these instructions in a program. That's our puzzle input, to tell the screen what to draw. So given this example, we would skip 1 cycle and not do anything, and then we would take 2 cycles to add 3 to the register. And then after another 2 cycles, we would add a -5, so we would be down to -2. Let's see. It starts, X I think starts at 1. Yeah, so we would go up to 4 and then down to -1. That's what it shows here. And so for each cycle, even while add X is processing, it seems like we would still want to look at those cycles. So maybe we can learn something by looking at the value of the X register throughout execution. For now, we need to consider the signal strength, which is the cycle number multiplied by the value of the X register. So during the 20th cycle and every 40 cycles after that, so the 20th and then just counting up from 40 from there. Okay, let's see what it's telling us of this list. The signal strengths can be determined by the following. During the 20th cycle, the X register has a value of 21. So the signal strength is 20 times 21. Yeah, and the 20th cycle is in the middle of the second add X. So add X has 2 cycles. The first one does nothing. Okay. The value of register X is the starting value plus all of the other add X values up to that point. Right? So we're counting these up. Yeah, so 21 is our second variable, and then 20 is the current cycle. So when we get up to the next time, it's going to be 60 times and then we're still going to just be adding up everything up else to that point. Okay. And then we need to take the sum of these signal strengths. So we need to store what the signal strength was at each of these kind of 40 intervals, store them up. Yeah, and we need to find the signal strength. Yeah, so we need to find the signal strength during each of these cycles and then sum them together. Okay, I think we can start going with that. I'm going to take the puzzle input and put it into our editor. Okay. Yeah, and the file is only 144 lines, but each we're tracking the cycles, so each of these no ops counts as one cycle, and the addx are two. So I'm sure we would end on the number that it shows. We need to check finally the 220th cycle. So that's probably as far as it goes. But we're not going to hard code any of these values. I think we'll just do it dynamically based on the list size. Okay, so what we need to do, looking at this input, we're going to need to track which cycle we're on. So probably an indexed loop of some sort. And then we're going to need a command for adding. And I don't think that the signal strength matters, which I don't think the index that we're on or the cycle that we're on matters, except for when we're multiplying out. Yeah. Register X has the value of 21 by the 20th cycle. So that would be somewhere around down here. Okay, so really what we're doing is we're just adding up all of these add X. We also need to figure out which one is the 20th cycle. Figure out what the total running count of these is up until that point, and then multiply it times our interval. So let's do that. So far I've had pretty good luck in these challenges by modeling out some sort of state machine. This one feels like I could get away with just a couple lists and maybe one iterator, but I think I'm going to model this off of something. Is it the cathode ray tube, or is it a CPU that we're modeling? Okay. I think we're modeling the CPU at this point. So let's create that class. The CPU is going to have the current clock cycle, and it starts at 0, I believe. I don't know if it said anything about that. Yeah, I would assume that we start at 0, and the first time we run something, then we would be on cycle 1. Sure, we'll go with that. And then the X register needs to be kind of a running value that gets updated with each command, so we will just call that X, I guess. What was it, register? Where did it say the X? Yeah. We'll just name it that. We might end up having to edit this for part 2, but one problem at a time. We're going to make a function for skipping a cycle. We'll call it that. And that will just increment the current cycle. And then we will have a function for, what is it, add x. Okay. We'll do that. And that will just, it'll take 2 cycles and then it will update x. I think at the end, yeah, so it takes 2 cycles to complete, and after the 2 cycles, the x register is increased. Okay, so it's going to take a variable value, let's call it that, and yeah, what do we need to do here? The current cycle will need to increase 1, and then some logic here maybe in between the cycles. And then the current cycle will go up again, and then that's where register X would be added up with the value. So this is kind of like a loose idea of what I'm going to do. We will start here with creating that CPU. Kind of go from there. I don't think it needs to be created with anything. So for each input, we're either going to do one of these things. So we need to parse the input. There's only a couple things it could be, and we can check if it's a no-op, or if it's not, then we will just split by the space. Yeah, so let's do a mapping there. We could probably just do the logic here for input, because we're just gonna do it once, I think, sequentially from the top to the bottom. So a single loop kind of makes sense here. And if the string is this, then we will do, oh, we need to do this after we made our CPU. Okay, so here, if it's a no-op, then we are going to no-op. If it is not a no-op, we are going to split the line by the space. And so we will say value. We're going to do a destructured declaration there. I don't think it matters what the, right, I don't think this matters. I think we just need to take the second value after the space. So we're going to do this. We're going to take the string and split it by a space. And what this does, this just gets rid of that first value that we don't care about, and then value is the second part. So then we would just execute that command where we would say add x with the value. And we need to make that an integer. I think that will work even with the negative. Yeah, and so we are going to need to do something, probably keep a state inside the CPU, because out here we don't really know what cycle or anything is happening. That's all tracked in here. So we'll probably have to make some extra counter for the calculations at those intervals. So we need to track at 20, index 20, and then also every 40 from there. So what would be a good way to count if that is our value? Okay, so what we can do is create a extension function on an int for calculating this logic, and we'll just say is at interval, and we'll return a Boolean from that. And I think we can just make this work the same for every number. We would just take the cycle, and if we add 20 to it, then we can just check if it's divisible by 40 evenly. So yeah, that should work. So if we take current cycle plus 20, so then the first time that it would count would be at cycle 20. And then again, it's 60 because 60 plus 20 is 80. So if this result, we can do a modulo of 40 is 0. So that's if we divide this by 40, what's the remainder? And let's try that. That's what we will always want to check at these points. We'll only want to do it after we update a value. So if we do it here, if we update the cycle, well, also I think we want to do it here. Yeah, so anytime cycle is updated, we want to check if we're at the interval. And we could probably have a separate function for that kind of uses this. We could say check for, what are we checking for? Check for signal strength. Okay. Yeah, so we'll say check for signal strength. And this won't return anything. What it'll do, I think we'll just have a list of signal strengths. List of, signal strengths. And we'll call it a mutable list of integers. So then when we go through here, we will always just check if the current cycle is at interval. So if it's 20 or 60 or any of those, then we will do this where we add. Okay, we're going to add signal strengths, and we will take the we're going to take the current cycle. I think it was multiplied, so current cycle, it would be 20 times the current register X. So current cycle times register X. Yeah, that's going to add a signal strength. I think so far so good. Yeah, let's do that. Anytime we update the current cycle, this would be a really good use of a observable. Let me see if I can do that here, because observable is going to run something every time this value changes. So if I could do that, I wouldn't have to add this function after every time we change the current cycle. What is the syntax for this? I think it would be like that, 0 initial value. So what I'm going to do, I'll just look this up real quick. Always something good in a tutorial is Googling how to do something. Okay, delegates, right. Yes, okay. We'll do that. So I think we have to say it's an int. We can use delegates. And observed, that was just from that example. So yeah, this should all get called anytime this changes. We will just check for signal strength anytime current cycle is updated. That makes it easy because here we could just increment it twice separately. Yeah, I think that's everything I need to do right now. These could be private. And what are we going to need to return at the end? We're going to need to return the sum of all of our signal strengths. So I think we could just do that here. CPU signal strengths sum. Okay, so let's run this. See what we get. Okay, this seems like a reasonable number, 15,000. We'll check it, and if there's any issues, then we can just jump into debugging. But I think I understood the problem, what it was looking for. It is too low, okay. So there is a problem. Yeah. This will just check it further here. We know that this is working because the value is not 0. We will just I'll pull up the sample data and see what's different there. Maybe I can follow along with what's happening. Okay, let's put that in here. And I will set a breakpoint. I want to check the first time that this is at an interval. Make sure that that's the right point. Okay, so at this point the register is 20. The register should be at 21. Register X was supposed to start at 1. And I knew that. Yeah, that was a mistake. Okay. So now we're going to retry this with our full input. And we got 16,480. Let's test that. Awesome. Yeah, so it helps to read the instructions. Let's move on to part 2. It seems like the X register controls the horizontal position of a sprite. Specifically, the sprite is 3 pixels wide, and the X register sets the horizontal position of the middle of that sprite. So in this system, there is no such thing as vertical positions. If the sprite's horizontal position plus its pixels where the CRT is currently drawing, then those pixels will be drawn. Okay. You count the pixel on the CRT, there's 40 pixels wide and 6 high. The CRT screen draws the top row of pixels left to right, then the row below that, and so on. The leftmost pixel in each row is in position 0, and the rightmost pixel in each row is position 39. So for the first time in this year's challenges, they are indexing by 0. Unlike the CPU, the CRT is tied closely to the clock circuit. The CRT draws a single pixel during each cycle, representing each pixel of the screen as a pound sign. Here are the cycles during which the first and last pixel in each row are drawn. So cycle 1 starts here, and it takes 40 cycles, because each cycle one new pixel is being drawn, and at the end we start here. Then it moves down to the next goes, so it takes 240 cycles for the entire screen to be drawn. By carefully timing the CPU instructions and the CRT drawing operations, you should be able to determine whether the sprite is visible the instant each pixel is drawn. If the sprite is positioned such that one of its 3 pixels is the pixel currently being drawn, the screen produces a lit pixel. So lit pixel is £, and otherwise the screen leaves the pixel dark, which would be a period. Okay, so the first few pixels from the larger example, this would be the first kind of example. So the position is these 3 here. So at the start of the cycle, we begin adding 15. And the CRT draws pixel in position 0. So this is what it looks like. And then during the second cycle, CRT draws the second pixel like this. Okay. End of cycle, finish executing adds X. So register X is now 16. Allowing the program to run to completion causes the CRT to produce the following image. All right. Great, so we are actually going to need to render this in our terminal because it will likely draw letters, and that's our output. So that's cool. Okay, so the sprite position's going to be represented by the register value, and we can see that with the register X starts at 1, but our pixel positions start at 0. So 1 is the middle of our sprite, and the sprite is 3 characters wide. So when the program starts running, at the start of the cycle, we start adding 15 to our register, but it takes 2 clock cycles to complete. So the CRT draws a pixel in position 0. Then during the second cycle, the CRT draws a pixel in position 1. So that's where it looks like. And now, when we end the cycle 2, we finish executing add 15. So drawing happens before we update the register. That's important to know. So now the register moves over here. So when we start drawing again, we'll just continue. And so at each step of the cycle, the CRT is going to draw the next line or the next index, but the only difference is whether it's overlapping, right? So this is where the sprite should be, and so over here, it's just going to add a dot, just like this. Here it's going to add another dot, and then when we finish moving the register, now it comes over here, so the next time we draw with the CRT, it's going to overlap with this first one. Oh, whoops, it's going to overlap with this first one and draw that pound. So we need to track not only where the sprite position is, but also where, and that's just the register. So we track the register and we'll know the sprite position is 1 below or above it. And so I don't think for this one, I don't think the signal strength matters. Because the register never got updated based on the signal strength. So what we can do here is just keep keep the current index of the sprite position, and every time we draw with the CRT, we'll check our current index, and we should only have a total number of cycles, but it doesn't matter. This should work for any dynamic cycle. The one thing to keep track of is how wide each line is. So we're going to have lists of 40 characters, right? And once we get to the end, then we're going to bump down to the next list. And we can do that with kind of a dynamic counter. But yeah, let's do that. And we are also going to want to print out this to the display, but we'll get to that in a minute. First, for the CPU logic, I think we can leave everything here the same. So for part 2, we will also create our CPU, and we'll do kind of everything else the same. The main difference being what we will care about at the end. And we can even make this part of the CPU probably. Just say CPU update, and we can put the line through. That way we have a little less clutter going on. So the update can handle doing these things. Parsing the string for one is probably a good job for the CPU. So all of these can be private then. The only thing that's exposed is updating with the line, which is a string. Okay, so if we do this, we can check, let's see, yeah, so CPU update, we'll do that for both of these. Just put them in a single line. Great. Now what can we do? Why does this say it's not used? Remove redundant. Oh, right, because we don't need to call it on an integer since we just have the member variable. Yeah, so now that what the CPU needs is to draw. It would probably be appropriate to have a separate class modeling the CRT in the real world, but we kind of need these cycles in the register, so I'm just going to include that logic in here. Yeah, that makes sense. So we'll put update up at the top. And so what we need is lists, and once we get to 40 characters, we create a new list, and so on. So we will make a representation for that, and it will be pixel grid. It will be a mutable list of mutable lists of these string. It could probably be characters, but we're going to do strings. And what we'll do is every time the current cycle updates, we need to draw kind of based on what's going on. And I think I said before it needs to happen before the signal strengths get updated. So we are going to put something here for, what should I call it? At every cycle, we need to draw. So we'll say draw to CRT. I think that makes sense. It'll be private. Draw to CRT. And it already has everything inside the class that it needs. And what does it need? Every time we draw a pixel, we need to know um, which position we're in. And so drawing is really just going to be updating, or it's going to be adding items to our lists one at a time. So draw to CRT, it needs to check if pixel grid last size is greater or equal to 40, then we need to, actually no, we'll do this at the end. So the first thing we'll do is pixel grid last. We're going to add a new character. We'll just do an empty string there. And then after we've added a character, if it is, if that pixel line is full, which is what this represents, if it's full, then we'll just add another line to the grid. We'll add a new immutable list. Actually, I think we do an empty list, empty array. I don't know why that doesn't work. Oh, because it needs to be mutable, right? That's fine. That's fine. We'll do this. Okay, so when we draw to the CRT, that's what we're going to do. And now we just need to decide which character we're adding. And that is where we need to know the current position is going to be the size. Yeah, so register X. What could register X be? Is it only 0 to 40? Let's see what it shows. What could these values ever be? Maybe register X only represents where on this line it is. That'd be cool. I'm going to just verify that in here. I'm going to take our full sample or our full data, and I am going to I'm going to sum up, or I'm going to make a list and just check what the max and minimum values for register X can be. So inside of here, that would be just temporary, but X values, mutable list of, oh, I need to make that a value. And that's going to be of integers. And so anytime register X is updated, which happens here, we are going to say X values gets register X. Okay. And it will start with 1. All right, I'm just going to run this and then print out what X values is. So for part 2, let's just do that because I don't want to make any assumptions. Print CPU xvals max, and we'll do the minimum. See what we get down here. Oh, we got an empty list. What happened there? Pixel grid last, right, because it's a mutable list. We didn't add one to start off with. I always forget this. That's okay. List of, mutable list of, make it string, like that. Okay. So we run it. Okay, it shows that -1 and 40. -1 and 40 are the values that it can be. 40 makes sense. -1 doesn't. When would it ever be -1? So I guess I'll just print out the list of them. Okay. Let's see what happens with those x values. Yeah, it goes down to -1 quite a few times. I don't think it shows what to do with those. Maybe, did I miss something? Maybe we would just treat x as, yeah, maybe it doesn't matter, right? It doesn't matter because if x is -1 and it's the middle, but I don't know why that would be because then 0, So here x is 1 and it's in the middle of this. Here, if it was 0, then it would be the first and the second, and if it's -1, then it would just be this first. Okay, that makes sense. Yeah, okay. So we'll just go with that. We're never going to use the x value as like an index operator. We are going to say our sprite positions. We'll make a function, I guess, for getting the sprite positions, and that'll be a range of the 3 with x in the middle. Get rid of x values too, we're done with that. Yeah. We'll make, I think we could do it on an integer. Oh, fun. Int get sprite range. And we will just make a range of integers or an int range like that. Okay, and return, maybe a range isn't good. We'll return a list of integers because we know the middle, we don't know the start or the end. We need to make this function call, so return a list of this -1, this, and this +1. Right? So anytime we get this range, we'll get these, and then we'll just want to check if our current kind of horizontal index is part of this. And if it is, then we'll print. Yeah, this was kind of a big detour from the logic we need to do here, but we just need to decide between pound sign or a period. And we'll just say if register x get sprite range contains our current index, which would be pixel grid last size. And we'll just make that a value. So pixel index, and we'll just put it to this. Pixel index, and we'll do the same thing down here. Okay. Great. So now if it is in the range, we're going to print the dollar or the pound sign. If it's not, we'll print a period. And okay. Then I think for our Part two, we should really just print those lines. Is that public grid? Yes, okay. For each, we're going to print the line, which it will be a list and it'll print across, so it should be what we want. Yeah, let's run that, see what happens. Oh, and what is going on here? Oh, right, this was temporary code. Get rid of that. Our output gives us this. Are those letters? Let's see. You know, oh, something's maybe not right. Oh, right, our index, there's probably one too many. So this last one would get shorter. I need to check if the index is 39. Maybe? Hmm. That doesn't feel right, but we'll run it and see if they're all the same size then. Yes, okay. Hmm. Well, okay. Let's clean this up so we don't have commas. That's kind of hard to read. So when we print this out, we are going to join them to strings with no separator, and then it will be a lot more condensed. Okay, that doesn't look like 4 uppercase characters. So what I'm going to do is debug and look at each step along with the sample data and just see that we're drawing the right things. So yeah, let's do that. I'm going to stop this though because it shouldn't be doing it for part one. I guess I could, it probably doesn't matter because the logic is the same. We're just returning different answers. So here, the pixel index, pixel grid has a size of 1. Pixel index is, right, okay, that's the problem. Our pixel index should start at 0. That might contribute to our problem here. Oh, that made it worse. Okay. So let's run this and see. Pixel index. Oh, right. I'm taking the size -1. Size was 0. Because pixel grid, yeah, okay. So the very first register X value, it starts at 1. Our current cycle is at 2. We should be checking this before we start our current cycle. We're going to need to draw it really anytime we update. Before this gets added, maybe it would be more appropriate to move it here. What would that change? So right now, current cycle is going to be 1. Register X is going to be 1, which lines up here. Okay. When we get to this again, now we're in the third cycle now. Right, and that's because it only happens when we call update. But no op and add X. Add X, okay. So we're just gonna move this inside of these, I guess, for now. add X. It should really happen before any current cycle gets updated. I think there. Yeah, let's run it. So now current cycle should be 1 and uh, register X should be 1. When it happens again, register X should still be 1. Current cycle is 2. That might have just been our problem. So we'll let it finish running. And now, yeah, there we go. Now we got the sample output. Okay, let's put our actual input back. Was this it? Yes, and there we go. I have capital letters. So I'm going to enter those in. Let me read those out. This was a fun challenge. Awesome. So that's it for today. I'll be back tomorrow with another video. Thanks for watching.